Hey guys, welcome to your last set of notes. Yay! We're going to be talking about similar solids and similar figures and actually some cool things that they have, some cool qualities that they have. So just as a reminder, similar polygons, it's if we had two triangles like this, two things that look exactly the same, they just look like they're enlarged or reduced. Again, think back to chapter 9. When we talked about enlargement and reduction, what were we talking about? Hopefully you're saying dilation. So this is actually another example of a dilation. So whenever we're talking about similar polygons, what do we remember about their sides and their angles? So their angles were congruent. So if these two polygons or if these two triangles were similar, those angles would be congruent. And the sides, or the corresponding sides, would be proportional, meaning we would have to set up a proportion to find any missing sides. So looking right along, so if we had two similar polygons and we had their areas, if we had the length of, let's say that this was 3 and this was 4 for this weird looking polygon up here, we could actually find the ratio of their volume, or their area, their volume. We're doing my 2D figures, sorry. We can actually find the area, or we could find the ratio of their area. So this was the ratio of their sides. So we had 3 to 4 as that ratio of their sides. We could actually find the ratio of their areas. All we would need to do is square them. So it would be a squared over b squared. So if I wanted to find the ratio of the area of those two polygons over there, all I would need to do was square the numerator and square the denominator. This would be 9 over 16. So this is actually the ratio of the areas of those polygons. Okay. Again, I apologize for being incredibly hard to read. So for example 1, even though it says example 4, it's actually example 1. I'm having a lot of typos. The ratio of the areas of figure A to B, so we have these two figures. No matter what they are, we have these two figures with the ratio of their sides being 3 to 4. So if I know that ratio, again, this is exactly the same as the one before. So let's change these numbers. I'm going to change them on your notes so you guys actually aren't going to see this. So I'm making it 5 to 2 because why not? So 5 to 2 is going to be the ratio of those sides. So how could I find the ratio of those areas? What would I need to do with 5 over 2? I would need to square them. So in order to do that, it would be 25 over 4. This is the ratio. So and this is the ratio of the areas. Okay? And again, for these ones, you do have to make sure that you are talking about units specifically. So with this particular problem, our units, since we're talking about area, is going to be units squared and units squared. Both of them. Here's your practice one. Go ahead and try it. If you're not quite sure how to do this one, if you hang on tight, we actually go over an example that's kind of like this one later on in this video. So it might be able to answer any questions. So you'll definitely be able to do this by the end of the video. So next part is talking about how do we determine whether we have two solids and how can we figure out if they're similar? Well, if we think back to what we were just talking about with similar figures, what were the two things that happened with similar 2D figures, so like triangles and stuff like that? We talked about corresponding angles being congruent and also corresponding sides being proportional, right? Well, if you think about solids, the only difference is they have another dimension. Well, then if we wanted to figure out if two solids were similar, all we would need to do is set up proportions just like we did in chapter 6. So all we're going to be doing is setting up proportions to see if those sides are proportional. So for this one, example 5, they're asking, are these figures similar? Well, we're given 3 and 4 and 10 and 5, so we need to figure out whether or not those two solids are proportional, or if they're similar. Well, if we think back to chapter 6, how did we figure out if two things were similar? Well, if we set up our proportions, so let's do it with our height over our radius. So 4 over 3 is equal to the height over our radius, which is equal to 10 over 5. Well, when we had these two fractions, if we cross multiplied, we should get the same exact number on either side of our equal sign. So when we cross multiply, we get 20, because that's 4 times 5, is equal to 3 times 10, which is equal to 30. Is 20 ever equal to 30? No. So are these two figures similar? And why aren't they similar? Because they're not proportional. Sides are not proportional. So for this one, in order for these to be similar, when we cross multiplied, these two numbers here should have been exactly the same. Okay? So go ahead and try practice 2 on your own. You should definitely be able to do it. Let's move on to surface area. So we talked about before, if we had two similar figures, so if we had two triangles or something like that, we could actually find the ratio of their areas. Well, we can actually do the same thing when we have 3D figures and we want to find the surface area ratio. And that is actually going to be the same thing as what we were talking about before. We're just going to square those sides, or that scale factor, whatever we found. So if I have these two cylinders in example 6, actually let me back up for a second. So let's say I have two figures and the scale factor of those sides are 5 to 3. So I have two figures and I want to find their surface area ratios. Again, kind of like what we did on our first example, all we need to do is square the ratio of those sides. So if I have 5/3, I need to square the ratio of those sides, and that would be 25 over 9. So this is actually the ratio of our surface area. And again, make sure you have your units. Okay? So just to clarify, that's exactly what we're talking about. We're talking about the ratio of the surface area. So, for example 6, we're given the surface area of these two figures. They want us to find the original scale factor, the scale factor of the sides. So we have to think about this a little bit backwards. So they want us to set it up with 1 on top and 2 on the bottom. So we've got 288 over 128. And I know that I want to find the scale factor of the sides. They gave us the scale factor of the surface area, and I know if I had the sides and I wanted to find the surface area, I would just square the sides. So what do you think we're going to do in order to find the scale factor of our original sides if we're given the surface area? Well, the opposite of squaring something would be to do what? Hopefully you're saying square rooting. So to go backwards, all I would need to do is square root the numerator and the denominator. So that would be, actually no. Gives you a decimal on the top. Gives you a decimal on the bottom too. So again, I think I'm just going to change these numbers. Ugh, I do not like these. So on your notes, you won't have to see this part. You're going to be like, oh my gosh, Miss Smith, you crazy person. So let's say our surface area for number 1 is 64 inches squared. And the surface area of number 2 is going to be 25 inches squared. Okay, so let's try this again. So we wanted it to be 1 over 2, and we were given the surface areas for each. So we've got 64 over 25. And again, I want to find the scale factor of my sides. So I know they have to be smaller than this, right? So I need to take the square root, and I get 8 over 5. So this is going to be the ratio of sides. Okay? Again, if you're confused, make sure you're writing down questions. So this is your practice 3. Go ahead and give this a whirl. They want you to find the surface area, so you should be working your way upward. Now that we went over this example problem, you should be able to do the first practice problem that I talked to you about. So, last thing to talk about are volume. So volume of two similar solids. So if we have two similar solids and we want to find the ratio of their volume, again, we're thinking of volume in 3 dimensions and surface area was in 2 dimensions. So if we think about that pattern, instead of it being area or A squared, it's going to be A and B cubed. So all we're going to do if we want to find the scale factor of the volumes, we just need to cube the sides, or the original scale factor. So for example 7, I want to pause on this one for a second because this one's a little reaching. So again, let's say that we had the side, or the original ratio was 1 to 4. Okay, so this first one was figure 1 and this one was figure 2. Now I wanted to find the volume. What would I do to 1 and 4? I would cube them. So 1 cubed to 4 cubed would be 1, and 4 cubed is 64. Okay? So that ratio of the volumes is 1 to 64. Okay, so with example 7, they gave us the scale factor of the surface area of 2 cones. Okay, so this is the surface area, okay? So we have to think back to those other formulas before we find out the surface area, or the scale factor of the volumes. So they gave us the surface area, they want the ratio of the sides and of the volume. So the first thing, let's find the sides. Again, we already know how to do this. So we've got 4 to 49. And this was our surface area. And I want to find the scale factor of our sides. So again, I want to make it smaller. So I'm going to take square root of both, just like we did on the previous example, and we've got 2 over 7. So this was the scale factor of our sides. But we're not done. They want us to find the scale factor of the volume. Well, what would I need to do with the original scale factor in order to find the scale factor of the volume? I would need to cube it. So I've got 2 cubed over 7 cubed, which would equal 8 over whatever 49 times 7 is. 343. Okay? And this is really, I think this is really neat, that this is a trick that you can use. So, here is your practice problem. Before I end today, I just have one overall diagram just so you can look at it. It might be a little bit easier to understand what exactly is going on. So, again, here's our scale factor for our sides. For surface area and volume. So I want to figure out how to go between them, okay? So we've got this general formula of scale factor of let's say it's x and y, okay? It doesn't really matter. We can put, well, I'll do it with numbers in a second. But again, if I wanted to go from scale factor of the sides, to surface area, I'm going to square it. So it'll be x squared and y squared. To go from the scale factor of my sides to the scale factor of my volume, I would, cube it. So it's going to be x cubed, y cubed. Okay? To work your way backwards, you have to think of those inverse operations. So to go from my surface area to my scale factor, I'm going to square root it. To go from my volume to my scale factor, I would need to cube root it, okay? And this is something, I hope that this is something that you can really, it can help you out a little bit to go between those three different pieces. Let's do an example together. Let's say we were given the volume, and let's say it was, I don't know, 125 over 8, okay? And I want to find each of these three things, okay? So this is volume, surface area, and sides. Okay? Notice that you can't just go from volume to surface area. There's no arrow that connects just this to this, okay? So we have to always move from either surface area or volume all the way over to our sides, okay? So to go from my volume to my sides, it's this big purple arrow. It's going to be cube root both of those. So cube root 8 is equal to 2, and the cube root of 125 is equal to 5. Okay, so we have our scale factor of our sides. Well, let's say I want to find the scale factor of the surface area. Now I'm moving forward. Now I'm making it bigger. So what do I need to do with the 5 and the 2? I need to square them. So I've got 5 squared is equal to 25, and 2 squared is equal to 4. So these are my three scale factors, okay? Hopefully this diagram makes a little bit more sense now that I went through it once. This is going to be something that's incredibly important and incredibly helpful for you on your SLO, okay? That was your last video. Congratulations. You learned everything, almost everything in geometry. Now we have to start reviewing. Yay! All right, I'll see you in class.